Hi, in this video I will be cooking 4 eggs in hot boiling water for different amounts of time. The purpose of this video is to show the chemistry and explain the chemistry that goes on when the egg is in boiling water, as well as how it relates to the physical change in properties of the egg. So for the first step of the procedure, you want to fill the pot with about, well, given the size of this bowl, we'd want to fill it about halfway with water. It depends on what size bowl you're using or pot you're using, but half should be enough to completely submerge the eggs in water while we're boiling. And once we have filled it, we'll put it on our stove, put it to high heat to get the water boiling as quickly as possible. And we'll also put the lid on to speed that process up. So the lid will help the water boil faster and cook the eggs faster because it traps the vapor inside this inside the pot, so that will effectively increase the pressure inside the system, which will also increase the temperature of the system. Therefore, the water will boil faster as well as the eggs will cook faster. With water enough to completely submerge the ice, or sorry, not submerge the ice, submerge the eggs. And now that we filled it up with water, we can just get some of our already broken up ice over here. Try not to spill and make a complete mess of your kitchen, like I am, but we'll just add a couple handfuls of ice. And the purpose of the ice is to immediately transfer the egg into there once it's done cooking for its allotted time. And this is because we want to halt the cooking process. So when the egg is cooking inside the boiling water, there's an endothermic reaction going on in which the contents of the egg is absorbing the heat energy from the boiling water, and which causes some kind of change, some kind of chemistry, which we'll go into later. But we want it to stop as soon as it is taken out of the hot water, so that we can directly relate the amount of time it was cooking to the change in the physical properties. So we want the process basically to stop immediately after we take it out of the boiling water, and that is why we put in the ice bath, so that it will cool down the egg immediately and stop that process of cooking. Okay, so now that the water is boiling, we're going to prepare around half a teaspoon or tablespoon of salt. That should be fine. And we're going to add it to our water bath, or boiling water. And the reason for adding the salt is so that when we put the eggs in there, it stays whole even if the shell cracks. And the reason why that is when the shell cracks, the salt water will come in contact with the content of the egg, and it will coagulate it on contact so that it won't spill out and make a liquid mess, and it will still hold that egg-like structure. And now that we've added our salt to our water, we can start to add our eggs in, and we should do this very carefully so that when we're dropping it, or when we're putting inside the water, the egg won't crack and it will have its integrity, and we won't spill any boiling water on us and risk any burns. So, as the eggs are cooking, we'll take eggs out in their allotted time intervals. So we'll take one egg out at 2 minutes, one egg out at 5 minutes, one egg out at 10 minutes, and one egg out at 15 minutes. And as we're taking the eggs out, we'll immediately have it transferred to the ice bath for the reason I explained earlier. So now that the eggs have been taken out of the ice bath and labeled with the amount of time that they were cooked for, we will begin to crack open the eggs and cut open the content to observe the inside. What is going on when we cook an egg by heating in boiling water is denaturing the proteins inside the egg. The yolk and white of the eggs are made up of a protein, which are long strands of amino acids. Proteins have hydrophobic and hydrophilic parts to their structure, and in their natural or native state, proteins assume a folded-like structure that have the hydrophilic portions on the outside and hydrophobic portions on the inside. This is due to the hydrophobic effect, where water, when in the presence of something that is hydrophobic, will organize itself around that structure in a neat arrangement. This would cause an increase in entropy due to the reduction of randomness of water from arranging itself around the hydrophobic structure. Just like how we saw entropy being a driving force in organic chemistry, such as the Riccio-Diels-Alder reaction, it is also a factor as to why proteins are structured the way they are in their native state. This is to avoid that increase in entropy by essentially hiding away its hydrophobic part away from exposure so that water won't be able to organize itself around its structure and cause an increase in entropy. Generally, an increase in entropy means decrease in randomness, which is unfavorable, and vice versa with decrease in entropy causing an increase in randomness, which is favorable. The endothermic denaturing of the protein is when enough heat is applied to the protein such that the bonds that the amino acids of the protein have with each other that make up the structure of the protein is broken such that the protein loses its structure and goes into an unfolded state. As the proteins of the egg begin to denature, they start to coagulate. This is why the content of the egg solidifies when it is cooked. The longer the egg is cooked, the more proteins denature and coagulate and become more solid-like. This is reflected in the states of the eggs cooked for different amounts of time. The protein of the egg that was only cooked for 2 minutes didn't denature as much as the eggs that were cooked for a longer time. As we can see from the 2 minute egg, there was large amounts of egg white that was uncooked because there wasn't enough heat that was applied to denature the proteins, and the yolk is almost completely uncooked, not even touched. While the 5 minute one, the outer layer of the egg whites is more cooked than in the 2 minute one due to the heat going from the outside inwards, because heat transfer from the shell towards from the outside traveling towards the center. There's more egg white cooked in the 5 minute egg, yet the yolk in the center is still very runny due to lack of denaturing and coagulation. In the 10 minute egg, we see a much more progressive denaturing that occurred within the egg, with all of the egg whites being completely solid and coagulated due to denaturing, while the same could be said for the egg yolk, although there's a gradient in the coloration of the egg yolk, which denotes a difference in uneven cooking, which basically means the outside of the egg yolk denatured more and coagulated more than the inside due to, again, heat going from the outside towards the center. In the 15-minute egg, we have this completely solid egg white with a completely solid and chalky colored yolk, signifying great denaturation and of the proteins in the egg. An interesting change is seen in the overcooked egg. The yolk took on, as you can see, the yolk took on a greener color on the outside here, on the very outside of the yolk. If we compare it to the yolk of the 15-minute one, we can see that this is still a relatively brighter yellow color, as opposed to the yolk of this 20-minute one. We see that it took on it's a little harder to see on camera, but it took on a darker, almost a green hue-like color on the surface of the egg yolk. And this is because a protein called phosphatin in the egg yolk complexes all the iron inside the yolk of the egg. And when the egg is overcooked, this causes the phosphatin to cleave and free the complex iron. This iron meets hydrogen sulfide, a compound that is also built up in the egg throughout overcooking through the excess heating. And the hydrogen sulfide is built up in the egg white. So when the free complex iron meets at the surface of the yolk and at the surface of the egg white, when it meets the hydrogen sulfide, the two react to form this insoluble iron sulfide, which is the reason for this color change we see in the egg yolk.